For those who don't know, I'm Mike Short of MIT. I can't see who all else is on the other line because everyone's been privacy muted, but I'd like to extend a welcome to all of you for coming to see the what I call Finding the Cure for CRUD, Insights from CASL. It's going to be a mix of simulations that our group has been doing as part of CASL and experiments that those simulations have inspired to try and not only understand how CRUD works, but how we can either stop it or bend it to our will. So I'd like to start out by giving some shout outs. A lot of people were involved in this work. I'm not going to claim that I've done even the majority of it. So first I want to say thanks. Well, I'm not going to read all the names. You can see them all here. What I'd like to point out is that a lot of this was orchestrated by Brian Kendrick, who's the lead MAMBA developer, and MAMBA is the name of the CRUD code that CASL is developing. The folks that are underlined are members of the MPO CRUD team, and what I actually want to point your attention to is how many folks aren't underlined but still made a major contribution to this work. It takes a lot of people to really solve a big problem like CRUD, and I think it takes this many to get even as far as we did right now. So I'd like to say thanks to you all, especially if some of you are listening right now. So I want to quick give a little aside and talk about a topic I call nuclear materials at the mesoscale. Mesoscale is sort of a buzzword that's come up a lot lately. It's sort of the middle length scale between the microscale and the macro scale. And I'll define what I think that means. The microscale is sort of on the level of atoms, unit processes, really small simulations, and sort of nanoscale experiments. It's what I'd call happens in a lab or in a computer, but isn't really measurable that easily in real life in a big system like a nuclear power plant. Whereas the macro scale is exactly what I just mentioned, the big system, the nuclear power plant. And in my opinion, a lot of the fundamental science happens down at the microscale level, whereas a lot of the technology happens up at the macro scale level. And it's sometimes hard for these two communities to make a handshake because the scale that they're separated from is vast, multiple orders of magnitude in length and time. And so there's this sort of fuzzy region in the middle, which we call the MSS or Mesoscale Science region, where the push from the science world to work on bigger simulations, longer time scales, more complex systems can be met by the pull from technology. Because eventually, if these codes can't be used to gauge the safety or operation of a plant, then they're not quite as useful to the industry as they should be. And a lot of the work that our group is doing is here in this mesoscale region. So for anyone who doesn't know, I'll give a quick intro to what is CRUD. It's actually a technical term. It's not just the stuff that you find on the bottom of your shoe. It actually stands for Chalk River Unidentified Deposits, after the Chalk River labs where they were first unidentified as this sort of blackish brownish sludge happening up on the fuel rods. They pretty much look like what you see here. This is a picture of an actual pressurized water reactor or PWR fuel assembly, and this brown gunk on them is the CRUD. If you zoom up close in, it ends up looking like a pretty porous layer, tends to about 100 microns thick, that has multiple levels of porosity. You can sort of see this nanoscale porosity where you can see little black dots amidst this gray stuff. And in addition, there are these black regions right here, which we call boiling chimneys or vapor chimneys. The way this stuff works is capillary action will cause water, which contains whatever else is in it, like boric acid, lithium hydroxide and such, to get sucked into the nanoscale pores of the CRUD. And the cladding underneath is quite hot from the fuel. It boils off the water, and the water shoots out of these vapor jets or boiling chimneys right here, leaving behind the other stuff, like the boric acid, like the lithium hydroxide. And so there's a number of problems that CRUD can cause in operating power plants, one of which is called the CRUD-induced power shift, or we just like to call it CIPS. This is when CRUD tends to form on the upper parts of the nuclear reactor, and so wherever there is CRUD, there's a lot of boric acid hiding out in the pores from that mechanism I just mentioned. And wherever there's lots of boric acid, the neutrons tend to get absorbed and the power spectrum shifts away from that region. And you can actually decrease the relative amount of power at the top of the core. Now this is a problem because the control rods that come in an emergency enter from the top. And so you actually lose shutdown margin when you get too much CRUD hiding out too much boron. Some plants have been forced to derate in the order of 10% power level to mitigate this effect. And when you lose 10% of your power, you lose about $1 million a week. There's a second effect that CRUD does, what we call CRUD-induced localized corrosion. As you can imagine, in between the water, which is out here, and the fuel cladding, usually there's nothing. On a clean piece of fuel cladding, the water can contact it and get good heat transfer going on. When there's CRUD, it can sometimes act as a thermal insulator or a thermal resistance, making the cladding underneath get hotter and also have higher concentrations of dissolved chemical species like boric acid and lithium hydroxide. And it can lead to these pinhole corrosion leaks. Wherever you get a hot spot, corrosion is going to speed up. Sort of a good benchmark is about every 15 Kelvin you go higher in temperature, corrosion is going to speed up by a factor of 2. And that doesn't even take into account extra chemical concentrations. So if you get one of these pinholes, which we call a silk leaker, you got to shut down your plant. And every day you're shut down, you lose about $1 million a day. And finally, this CRUD, which is made of mostly nickel and iron oxides, will transmute into other isotopes, including things like cobalt-59, nickel, I think 58, and so on. And that causes a whole lot more of a dose for folks that work on the primary circuit of a pressurized water reactor. So there's a lot of problems that CRUD causes, and part of the goal of CASL is for us to be able to predict the effects of CRUD so we can understand how it forms and what to expect. In terms of the anatomy of CRUD, how it forms in the first place, the theory that most of us are going with is there's all these little nucleation sites on fuel cladding. These can be asperities, secondary particles, scratches, who knows what, something that isn't smooth, that helps bubbles nucleate at those places. And so when a bubble starts to form, you get a little bubble of gas right here, and there's a layer of liquid trapped underneath. That liquid contains things like boric acid, lithium hydroxide, and iron and nickel oxides. It sometimes happens that if the bubble gets awfully big, the fluid can't escape. And so it ends up that the water evaporates into the bubble, leaving behind a little coffee ring stain of CRUD, a really thin layer. And as these layers build up higher and higher and higher, you start to see the pictures like what you see here. From the top, you can see that CRUD is pretty irregular. These black holes right here are those boiling chimneys or the vapor jets that I mentioned before. And from the side, you can see these vapor jets pretty clearly as these empty areas where there would have been vapor shooting out. And so, unlike a lot of operating history in nuclear power plants, CASL has decided to take a very scientific approach to understanding the CRUD problem. You can sort of approach it in two ways. You can take what I call the sledgehammer approach, where you shake it off, scrape it off, take it out, break it off. Or you can understand at many length scales what the scientific explanation is for CRUD occurring. So at the same time, we're doing atomistics of CRUD and, in my group, CRUD-resistant materials. And we're trying to validate those simulations with experiments. So in our group, we're actually trying to grow CRUD in the lab, and I'll explain a little bit more at the end of this talk, and see if these results correspond with the simulations at the atomistic level. Up at the mesoscale, which is that middle scale I talked about, we have the MAMBA model, specifically my part, which is known as MAMBA-BDM, for boron deposition model. And for those who don't know, this is a picture of a green mamba, so the logo of our code. And at the same time, we're actually building a flow loop, much like the Westinghouse Walt loop, where we can grow CRUD in prototypical PWR conditions, with the addition that we're going to have a bunch of viewing windows on the side. These are sapphire, diamond-coated windows that can survive 350 Celsius and 15 megapascals of pressure. So we can actually watch CRUD grow in real time for what I believe is the first time, at least the first time in the open published literature. And we're also looking at silk, or CRUD-induced localized corrosion. A student of mine, Andrew Dyquist, is working on the hognose model, which is a new model to look at zirconium oxide corrosion, which takes into account what we call breakaway oxidation, where you can have oxidation happen at a slow rate and suddenly it speeds up. And you can couple this hognose code to the MAMBA-BDM code and actually start to simulate CRUD and corrosion together. But it doesn't stop there. We can actually start to run these experiments in that PWR loop I mentioned. In addition to growing the CRUD in the loop, we can cut the rods apart at the end of the experiment and measure what the corrosion thickness is. So we can actually validate all the different models at all the different length scales with a whole bunch of experiments that we're setting up here at MIT and elsewhere. So I want to go over an overview of the CASL approach to CRUD. It's inherently multi-scale, it's inherently coupled, and that's what makes it kind of new and exciting, especially to someone like me, who I only finished grad school 3 years ago. And I was always told, all right, we're going to study these heat transfer models, and we're going to assume everything is 1D, isotropic, adiabatic, isobaric, assumption, assumption, assumption. And then when you ask, okay, well, what do you do when things get harder? The profs would usually say, oh, that's when you have to use computers. Well, this is when we actually get to use those computers. And so all these things I was wondering, how do people actually do this stuff? CASL's doing it for real. We have a top-down approach where the ultimate goal is to make a 3D full-core engineering CRUD framework called MAMBA, being developed by Brian Kendrick and John Barber at Los Alamos. And the goal is to predict the CRUD thickness, the peak clad temperature, and the boron loading at every point in the core, and actually couple it to fuel performance codes like Bison, Peregrine, and anything else you'd want to use. Now, this MAMBA framework gets information at a much higher fidelity, but at a smaller length scale from the MAMBA-BDM code. Now, the MAMBA-BDM code works over here on the length scale of 1 to 100 microns. You wouldn't want to run this sort of simulation on a full core, where the fuel rods are 4 meters long, and there's a whole lot of them. So what MAMBA does is looks at what's called regions of interest, places where it would think the boron loading is the highest, or the peak clad temperature is the hottest, and says, hey, MAMBA-BDM, what's going on at the microscale here, in the mesoscale? So it couples CRUD cladding to cladding corrosion. It's a much higher computational cost, but you get more accuracy. And there's a trade-off between running this MAMBA-BDM model at a few places in the core and running MAMBA everywhere. We want to get the most bang for our buck. And in addition, we have atomistic and thermodynamic simulations, which are filling in a lot of missing fundamental data. As we started to build these MAMBA and MAMBA-BDM models, we realized there's some missing material properties that nobody has bothered to look at, like the thermal conductivity of nickel iron oxide. It's most of what makes up CRUD in some cases, and yet nobody has bothered to measure its thermal conductivity. So we're pre-computing a lot of missing fundamental data and passing the info up to MAMBA-BDM and to MAMBA through BDM. And so in this way, the length scales are all coupled. We choose which ones to run side by side and which ones to pre-compute to get the most information out of the least number of CPU hours. I'll give a quick overview of the MAMBA code. Now, since I didn't develop it, I don't want to butcher the models inside. I'll just tell you what's going on generally. It's a much higher length scale code where the nodes can be on the order of about 1 centimeter. And so if you see over on the left, the microstructure of CRUD has granularity at the 1 to 100 micron level. So while MAMBA doesn't capture the full detailed microstructure of CRUD, it doesn't have to, because we don't need that detailed of information throughout the entire core. There is sort of a gap between stuff going on at the centimeter level and stuff going on at the micron level. And that's where MAMBA-BDM comes in, and that's frankly the only part that I'm qualified to talk to you about as an expert, since I wrote it. So what MAMBA-BDM does in its simplest form is it assumes that there's this smallest repeatable unit of CRUD. We just look at one boiling chimney, one cylindrical boiling chimney, and a revolved cylinder of CRUD around it. And we can start to compute things like the detailed temperature in the CRUD or the fluid velocity or other things, and start to look at where are the hot spots in this CRUD and how hot do they get. Keeping in mind that a difference of 5 Kelvin actually makes a big difference. That could be a 25 to 30% change in corrosion rate, which you want to know for your corrosion margin. I'll just get into a little bit of nitty-gritty, especially for you students out there, to see what sort of equations go into a model like this. I'm going to give the example of the temperature equations. And although I say this is the temperature equation, notice there's pressure in here. What makes MAMBA-BDM fairly special compared to some previous CRUD models, not all of them, is that the equations are all fully coupled. You can't solve the temperature distribution without the pressure distribution. This isn't one of those separation of variables problems, because in addition to the equations being difficult, the simulation space or the mesh can be quite difficult. There's no analytical solution that I could compute in my lifetime. So what we look at in this is it's a combination of conduction, which is measured by this thermal diffusion term, and convection, which is measured by this term right here. And this stuff in the parentheses, the gradient of pressure times some material properties, that's just the fluid velocity coming through the CRUD. So we define our simulation volume with a constitutive partial differential equation, or a PDE, along with a number of boundary conditions, or BCs. And over here is a table of symbols because I use quite a lot of them. Now you might notice there's a lot of material properties. In its simplest form, you could assume that these are constant. But that would be too easy for CASL. We actually want full fidelity and a whole lot more full coupling than a lot of previous models. So I decided instead of modeling CRUD as a sphered mass or a smeared mass or something simple, it seemed to me that CRUD is quite fractal in nature, which is to say it's a sort of self-repeating structure over a certain number of length scales or a certain size distribution. You can keep zooming into CRUD if you were looking in an electron microscope, and it looks kind of the same. It's made up of lots of different crystals of mostly the same components of different sizes. And so when something is self-similar over a few length scales, you can reduce the full complexity of its geometry down to a few things called fractal dimensions. So what we start with is a porosity of the CRUD, which we can either calculate or we can measure from electron micrographs, as well as pore sizes, where we can take actual CRUD flakes and measure what are the average and distribution of the size of the holes in the CRUD. We then compute what's called a pore tortuosity, which is a measure of how twisted the fluid paths are in the CRUD. A tortuosity of 1 means it's traveling in a straight line, which would be like through a straight pipe. A higher tortuosity means it has to take a much more twisty, curvy path to go a certain amount of distance. We can use this information to compute two fractal dimensions, what's known as the free area dimension and the tortuosity dimension. So in this simulation, if I was simulating a two-dimensional slice of CRUD, you end up with these fractal dimensions in what's called a reduced dimensionality, where if the fluid was free to move in any direction in 2D, we would say that would be a two-dimensional space. And if you have a tortuosity that's a little bit higher, it's almost like it's a 1-point-something dimensional space where the fluid can move. It's sort of an approximation. It's kind of hard to wrap your head around, but the math pretty much works out. And we can use these fractal dimensions to calculate actual material properties of the CRUD, like the thermal conductivity of two-phase in the CRUD, or actually even three-phase. The mixture of solid, liquid, and gas, you can approximate it as a full-out thermal conductivity. And the equations I know are pretty hairy, but once they're under the hood, they just work, and we can treat them like a black box unless we notice something wrong. The fun doesn't stop there. When we were looking to compute the two-phase thermal conductivity of CRUD, we had to look into which species actually make up CRUD. And so we saw that usually it's something like nickel, nickel oxide, iron oxide, nickel iron oxide, which is known as nickel ferrite or trevorite, and zirconium oxide. And when it came to looking up the thermal conductivities, I found expressions for 4 of the 5 of them. One was unknown. No matter how hard we looked and the ceramics experts at Los Alamos looked, couldn't find it. So we made an assumption that it's about 8 watts per meter Kelvin, based on other similar spinel structures. And it turns out that it's the major constituent of very much CRUD. As a 10-year experimentalist, I was completely unsatisfied with this, and so it's time for some experiments. So I spent a week, headed out to Los Alamos, and the experts there actually grew single crystals of NiFe2O4, performed a whole bunch of different measurements on them. So they performed measurements of density, the change in density with temperature, heat capacity versus temperature, and thermal diffusivity versus temperature. And I'll just point out that some of this is about to come out in a paper that we're going to submit soon, so stay tuned. I'll also mention for those listening on the video, this is unpublished work, so please don't reproduce it until we say you can. And if you multiply those 3 parameters together, you get the thermal conductivity of nickel ferrite. And so on this graph, I graphed this red dotted line, which is our old assumed value, and what you actually get. It's like half as big as we thought it was, or as we assumed it was, over CRUD relevant temperatures. And so rerunning some of the simulations, it brought down the effective thermal conductivity of this two-phase CRUD from about 5 watts per meter Kelvin to about 4 watts per meter Kelvin. That's a serious difference. And this measurement would not have happened if CASL hadn't sat down and said, let's do CRUD out the fully coupled way, and made us look and see what's the thermal conductivity of every phase. Look at that, there's one missing. So back to the simulations. I'll show a couple of examples from 2D results. what I did is I took some normal reactor operating parameters, so typical heat flux, coolant, temperature, pressure, et cetera, and I started to look at the distribution of temperature through this little slice of crud that you can see right here. As we expected, that the boiling chimneys, where we assume boiling takes place, pegs the temperature at the boiling temperature. So T equals Tsat, which means that the temperature doesn't exceed the boiling temperature. Away from the crud and at the cladding, it gets quite a bit hotter. So there's a temperature drop of about 15 Kelvin across this crud. We also started to look at some assumptions that people had made in previous models about crud. One of them was that the fluid inside crud, because it has to squeeze through these nano-sized pores, moves so slowly that the effect of convection, or fluid carrying heat itself, can be completely ignored. Well, there's actually a dimensionless number which you can use to characterize the ratio between conduction and convection. It's called the Peclet number, which is exactly the ratio I mentioned before. And a ratio of 1 means they're about equal strength. In a lot of the crud, this ratio is, 0.3, 0.5, which is to say convection is not negligible. And down when you get into these regions, convection actually outpaces conduction as a heat transfer mechanism. And what we found is that assumptions had been that the fluid runs on about half a millimeter per second. And we're finding it to be 30 times faster than that, now that we've done these high fidelity, fully coupled microscale simulations. And so we started to look at the effect of what does turning on or off convection in these simulations do to the peak cladding temperature. We looked at two cases, which are on the curves right here, when the boiling chimneys are fairly widely spaced apart, about 25 microns core to core. You can see that these two curves, the solid and the dotted line, are basically on top of each other, which is to say there's almost no effect. As the boiling chimneys get closer, these curves start to diverge. So when the chimneys are about 10 microns from core to core, which is a lot of what you see right here, there can be a difference of, oh my God, 2 Kelvin. Doesn't sound like a lot until you do the corrosion calculations, and it comes out to a 10 to 15% change in corrosion rate. And when your corrosion margin could limit whether or not you can run this reactor, you want to know things to within 10 or 15%. At least I would. And so now we can start to get a little more complicated. I quickly grew tired of simulating rectangles and wanted to get into something a little more realistic. So we can simulate in 3D the effect of this actual geometry and things like the corners on what the peak clad temperature is underneath the crud. Because we make some different assumptions in 2D and 3D. In 2 dimensions, we assume what's called symmetric boundary conditions, where there are 0 flux boundary conditions between this slice of crud and the one that we assume is right next to it. In 3D, we assume periodic boundary conditions, which are not exactly the same. And what I did is I ran a scripted set of about 80,000 simulations at different crud thicknesses and temperatures to see what's the difference between 2D and 3D. And by the way, the 2D simulation ran in like 8 seconds, and the 3D simulation would usually run in about, sorry for the slide jumping, would run in about 30 to 120 seconds. And what we found is that when the crud was rather thin or rather thick, there was quite a large difference, maybe 4 or 5 Kelvin, between the predicted 2D and 3D peak clad temperature. And when the crud is, 30 to 50 microns, there's not much of a difference, less than a Kelvin. So when the macro scale MAMBA code calls BDM and says, hey, what's the peak clad temperature underneath this crud? BDM will know, do I have to do a full out 3D simulation, or can I do a simplified 2D simulation and make it close enough? Which means you get a good enough answer in less time. We can also look at much more realistic geometries. So what we did here is took a picture of a crud flake from the literature, from a report from EPRI, extracted its boundaries using a few image processing tools called GIMP and Blender, which are open source things you can find yourself, created a geometry adaptive mesh in Qubit, and applied the equation set from MAMBA to that mesh to figure out what was actually happening underneath this crud flake in this actual power plant. The results we got were quite interesting. We found that wherever there was a boiling chimney, we got these blue areas, because boiling, or phase transfer, helps keep the cladding cool. Whereas away from the cladding, we got these hot spots. It's interesting because there was a patent issued in the early 2000s that said, hey, let's electropolish the fuel cladding get rid of the nucleation site, and slow down the formation of CRUD. Well, I'd like to counter with, you can always fight the laws of thermodynamics, but you can't win. Eventually, you're probably going to start to grow some CRUD. And when you do, you'd better hope that there's a lot of these vapor chimneys to help keep the CRUD cool. We also looked at pressure in 3D. What I've plotted here are a bunch of 3D isobars, or equal pressure lines. And when you see a flat plane like this, it means that the CRUD is moving perpendicular, that the fluid in the CRUD is moving perpendicular to the plane or straight down. Only in the bottom 10 or 15 microns does it start to take a curve into these boiling chimneys. And what this tells us is even when the CRUD gets thicker, the bottom 15 or 20 microns of CRUD is about where all of the steaming or boiling takes place. And we found the same sort of thing to happen in the macro scale models for MAMBA. And finally, we can start to predict where precipitation would occur in the CRUD. I did mention that the CRUD will fill up with boric acid. Now, boric acid is quite soluble in water, but it does have a finite solubility. And a lot of boron compounds exhibit what's called retrograde solubility, which means as the temperature goes up, the solubility goes down. It's sort of a counterintuitive thing. And so as the temperature goes up, this region of precipitation can grow, and then you've got a solid mass preventing water and boiling from getting down to the cladding to cool it off. And that's when you can have a real bad day. And we're still working on a lot of these chemistry models. We're actually waiting for a bit of thermodynamic data from the microscale where we can start to predict the formation and precipitation of other phases within the CRUD. And here's where things get really exciting. What we've done here is done a mesoscale to full core simulation, where on the same graph, we managed to get a simulation output using CASL models and an actual plot from a plant of boron levels. Now you might notice the agreement is not so good. That's okay. Just the very fact that we can get these two things on the same curve means we have a starting point where we can start to tweak our mesoscale models and actually see their effect on the macro scale and try and get the simulation curve to match this curve right here. And I wanted to show a quick movie of this simulation in action. What this is actually doing is using something along 20,000 single simulations of MAMBA-BDM at different points in this full core. Over on the left, what you can see is a power distribution, or a fissioning rate distribution, and the single plot right here is an axial power distribution. Then the middle right here is a buildup of boron that's computed by MAMBA-BDM, and on the right here are CRUD thicknesses taken at 6 different points along one of the fuel rods. And if you watch this axial power distribution as the simulation progresses, you'll see that as the boron builds up near the top of the core, it starts to shift down. And that's the actual effect we're looking to capture. We clearly haven't captured it well enough, as you can see by the wide disparity between these two curves, but we have a starting point, which means we can try things on the mesoscale and see them get better on the macro scale. We're also linking CRUD and corrosion. So this is my student Andrew Dyquist, who's been building the hognose model that I'll talk about a little bit for now. We started off with some fundamental thermodynamics data, the zirconium-oxygen phase diagram, as computed by Anton van der Ven. He then gave us some diffusivities as functions of temperature, where we were able to extract piecewise and fit cubic splines to. For those who don't know, a cubic spline is a series of cubic polynomials whose derivative and values are continuous at every point. And having nice continuous things like this instead of a choppy piecewise function makes it a lot easier for simulations to deal with. We use those diffusion coefficients and start to compute things like how quickly does oxygen diffuse from the CRUD into the oxide, and what sort of phase changes happen within the oxide. And we can even take into account things like compressive stress from the metal-oxide interface and figure out when do we get runaway corrosion in zirconium oxide. And I have some results that aren't ready to show, but to say a preview, we're finding that there's a certain temperature beyond which corrosion sort of takes a runaway. And if we put CRUD on top of that, the same coolant temperature would cause runaway corrosion more quickly with CRUD on top due to its thermal resistance. And so we'll have some results of that coming out in the next few months. And so now on to the experiment. So like I said, I'm an experimentalist by training. And even though I made these models and they produce these rainbow pictures, I'll be the last one to trust my own work until I see it in the real world. And so what we started to do is say, hey, if we can understand how CRUD forms in simulations, we should be able to develop materials that can actually stop it from forming in the first place. So what we'd like to do is engineer some sort of coating or surface modification that makes that first layer of CRUD not willing to deposit. And so what we've done is, on a bit of a shoestring budget at first, we produced this pool boiling facility that has some control stuff you see here I won't get into. What I will say is it's got a heater on the inside, sealed up in this rubber gasket system, temperature sensors called thermocouples and pH sensors, and we have some little samples of materials that we test for CRUD resistance. And we'll look through this big hole right here with a camera to see where is the bubbling occurring, where's the subcool boiling happening like it does in a plant, just at a lower pressure temperature, and does that correspond to CRUD spots? And I'd like to mention also the generous funding from EPRI for this project. So this is a picture of the samples before boiling. Notice they're pretty clean. What we've got here is a little chunk of zircaloy 4, which was a common cladding material, diamond-like carbon, which was chosen for its low surface energy, aluminum oxide or single crystal sapphire, chosen for its high surface energy, and zirconium carbide, a piece of which was actually left over from an undergrad project of mine about 10 years ago. And this is what they look like after about an hour of boiling in water with boric acid and lithium hydroxide, just at ambient conditions, 100 Celsius and atmospheric pressure. You start to see these little spots forming wherever there were bubbles. And these spots are like proto-boiling chimneys for CRUD, except on zirconium carbide. We ran this a couple times and couldn't get these spots to form. So we start to look a little closer. We saw, and hopefully this animation's coming through on all your guys' huddles. It's pretty sweet in 1080p over here. What we found is that we started off with these tiny nanoparticles of nickel oxide and iron oxide. And the CRUD that grew on the surface looked completely different. These 20 nanometer particles have reconfigured somehow into these 5 to 10 micron plates that are like 5 or 10 nanometers thin. And the size of that circle spot that you saw right there is about the diameter of a bubble. So wherever there was a bubble forming, we have one of these spots. And the CRUD at the center of the bubble was pretty thick. You might also notice at the periphery of these bubbles, you can see these white regions. So we decided to look and see what's that all about. If you zoom in, all of those plates are still there. They've just been blown down. And what we think might be happening is as these bubbles form on a surface where the wall temperature is higher than the boiling temperature and they detach, they go into the subcooled coolant and they collapse. The collapse generates a little cavitation shock wave that we think blows down these platelets. If any of you guys have boiled water for tea or coffee in an old-fashioned kettle, you'll notice that it starts getting really loud, and as soon as real boiling happens, it gets quiet. That loudness you hear is actually bubble collapse shock waves, pressure waves you can hear from subcooled boiling that we've been recreating here in the lab. And so to show you what some of this CRUD looks like, we've been able to recreate some of this sort of needles and forest of platelets and things that we saw in nuclear plants, except the spots are a whole lot bigger. And the reason for that is probably that the size of a bubble at atmospheric conditions is around 500 to 1,000 microns, which coincidentally is about the size of the spots we're growing. So we took a focused ion beam, or a FIB for short, sliced this CRUD through, and we want to look and see what does the bond between the CRUD and the underlying substrate look like. And on titanium oxide, it's a very good bond, which is very bad. What we don't want is to form this really sticky, tenacious bond. It's pretty characteristic of what's called tenacious CRUD, which is CRUD that resists things like scraping and ultrasonic cleaning in actual nuclear plants. When we looked at zircaloy 4, our control material, same thing. The CRUD up here formed a nice solid bond between it and the zircaloy. When we went to zirconium carbide, which if you remember didn't form any of those spots, we noticed two interesting things. One of which is that those little original nanoparticles that we started with are still there. We don't have a forest of those needles. And second is that if wherever there were these big particles of nickel and iron oxide, they were still made of the original nanoparticles, and we couldn't see a bond. We kept slicing slices at very shallow planes to see were we missing a bond. We couldn't find one. Now, I'm not going to say that this works yet, because I'm an experimentalist, and I don't believe things until you repeat it 5 times, and then somebody else repeats it 5 times, and somebody else repeats it. But it's a lead. It's something that might work. And we have other things going on. I mentioned at the beginning of our talk that we're developing a pressurized water reactor CRUD loop. We've actually got about half of it done, where you can see right here this complicated mess of piping that measures water chemistry being developed by my student Pun. And we're also looking to try and control the way that boiling chimneys form from my student Li Lin here. What we actually want to happen, according to our simulations, is to grow CRUD that looks like this, with lots of chimneys to keep it cool. Not like this, where there are very few chimneys and it acts like a solid mass of thermal resistance. So we'll get a little bit into how we're making this CRUD loop. How are we going to validate the models in MAMBA-BDM? Simulation is a lot easier than the experiment's going to be. In the simulation, you just put some equations together, hit go, and view the rainbow, the pictures that come out. In the experiments, we've got to take an autoclave, which is a heated pressure vessel of solid 316 stainless steel. And we're going to have these windows right here, and the only material that you can see through and holds up its strength is single crystal sapphire. But sapphire is corroded by high pressure water, so we have to add a film of diamond to it. But that way, as the CRUD inside this rod builds up, we'll actually have a heating rod on the inside. We can watch through this window and shine a light through the other windows and actually see the CRUD build as a function of time and compare it to what the models in MAMBA-BDM predict. And so we did some quick computational fluid dynamics analysis to see, will adding these windows screw up our flow profile? You'd think you'd want the flow lines to be nice and straight, and that if you had a window, you might create some turbulent eddies. Luckily, we found that's not the case, as long as you stagger the position of the windows up the autoclave. So if you have a bunch of windows which are collinear, the flow patterns interfere with each other, and the only part that you'd be seeing is the part of the flow that gets screwed up. If you alternate the placement of the windows, that effect goes away. So we have simulations telling us that what we see is probably what we want to see. And this is a diagram of what the loop would look like. We have a water tank that's going to have our simulated pressurized water reactor water go through a pressurizing pump, through a pressurizer, which is just a tank half full of water, half full of gas. It's like a pressure buffer. It's going to go through some heaters, temperature sensors, through the autoclave that has our CRUD-resistant materials, past some safety systems, and into a bunch of measurement equipment, and back around very, very fast to not only approximate the same temperature and pressure as in a reactor, but also approximate the same flow parameters, things like the Reynolds number and the Sherwood number. And now we can get really quantitative. When we want to say what makes a material CRUD resistant, on the mesoscale, it's does it grow CRUD or not. On the nanoscale, you've got to have a parameter that you can quantify. And so we found one of these. You can actually use an atomic force microscope, which is a type of probe where you've got a little cantilever tip with some sort of a probe on the bottom that you can touch down to the surface of a sample and either drag past it to sense topology or touch it down and pull back and measure the force of adhesion on the nanonewton level. And the way this works in what's called force spectroscopy mode is you take your AFM tip, or atomic force microscope tip, attach a particle of CRUD to it. So you've actually got a little CRUD probe, bring it down to the surface while shining a laser off the back. And that angle of the laser tells you how much this cantilever is deflected. And that deflection can give you a hint as to the force that's being applied to it. And as you pull back from the surface, if there's no adhesion, the probe will just separate. If there is adhesion, you'll be yanking on this probe, and it's not going to want to separate till it pops off. And you can generate the curves that you see over here on the right. The black curve is what's known as a loading curve. This is the force applied when you're pushing the probe down to the surface. And the red curve, or the unloading curve, is what happens when you pull it back up. And this difference, this area right here, gives you an adhesion force. And so what we're finding is intriguing us. When we look at titanium dioxide, which has a pretty similar chemistry to zirconium oxide, and diamond-like carbon, which are two materials with high and low surface energies, they're like right on top of each other, which we know it would not have expected. I would have thought that surface energy would have had something to do with CRUD tenacity. We appear to be wrong. In addition, something totally unexpected happened. The longer this probe sits on the surface, the stronger this force gets. And this could mean that as the particle sits on the surface with forces of nanonewtons, something is causing a stronger bond to form. And so we're running this now with a lot of different constituents of the CRUD and a lot of different CRUD-resistant materials to see which ones are actually CRUD-resistant. And do the AFM experiments correspond with the pool boiling experiments? And I just want to sum up with a quick aside. This problem of CRUD that we're studying is not unique to nuclear reactors. It's unique in the radiation aspect of it, but otherwise it shares a lot of principles with many other things. It's basically deposition where you don't want it to be, which otherwise known as fouling. And we see this happening all the time in oil heat exchangers where you get these asphaltene deposits or crude oil deposits. You can get microbial attack where bacterial attack can cause things to stick to stainless steel pipelines. And even on solar cells, you get dust accumulation where you don't want it. And to me, CRUD and dust and microbe attack and fouling and deposition are all sides of the same multi-sided Dungeons and Dragons die. It's the same problem with a different application area, only we reactor folks have it a little harder because we have to deal with radiation. So to summarize, CASL is building multi-scale CRUD models. Whoops, I don't know what happened there. Let's see, that should still work. Okay, if you can still see the slide, CASL is building multi-scale CRUD models all the way from the macro scale to the mesoscale to the microscale. We're already seeing success in coupling them, and we're also looking to validate them. Because what good is a model unless you know it's true? And so the way you know it's true is by running side-by-side model comparisons and experiments to see is what you're simulating in the computer actually correspond to real life. So thanks a lot for listening, and I'd like to open it up to any questions at this point.